So yeah, our product is called SuperTemp.AI. And for some quick background, so there's these materials called superconductors, and they have the ability to conduct electricity without losing energy when they're cooled below a certain temperature. This temperature is known as the critical temperature. There's many applications to superconductors like MRI machines, supercomputing, and electromagnetism. As of now, there's no efficient method to finding the critical temperatures of superconductors. So material scientists have to guess and text, guess and check critical temperatures, which takes much more longer than it needs to. We decided to tackle this problem with machine learning. So we found a data set on the University of Irvine's catalog called Superconductivity dataset, and it had over 84 columns and over 21,000 rows. Obviously, we can't use all of this data, so we had to use a method called feature selection, and we used a random forest model to narrow down these 84 columns into just 10 columns, the most important columns. These columns included inputs like atomic mass, electron valency, and thermal conductivity, and our target column was critical temperature. So we tried many different models, including random forest, MLP regressors, and neural networks, and we we found out that the best performing was the random forest model. So it had an accuracy of 91.6%, and after optimization, we found it had an accuracy of 92%. Here is a screenshot of our data, and this is the pre-processing to find the 10 most important features. And here are the results of our model. So here's some visualizations. So we had over 82 columns in our data set, and we did a feature importance test to find the most important features. So here's the ranking of the most important feature to the least important feature. And out of all of these, we took the top 10 most important. With these top 10 most important features, we made a heat map to see the correlation between the variables. And as you can see, there's not much correlation between each variable, except with each variable in itself. And this is a good thing because it means that they won't kind of cancel each other out when they're trying to influence the target variable. We took these top 10 most important variables and plotted them against our target variable critical temperature in a 3D scatter plot, just to see the relationship in a 3D scale. And then here's the distribution of the top 10 most important features. And we did this graph to find if any of the variables were categorical. And most of them are continuous, except this one, which looks categorical. But because of these outliers, we kept it continuous. Here are some model graphs. So this is a random forest model, and this is a decision tree model. As you can see, the random forest model has more logic gates, which is why in the end it performed better than the decision tree. So here are some scatter plots of all of our models, all of the 8 models, and we plotted their predictions against the actual true values. And in these graphs, you want to see a linear relationship, which shows the model is accurate. So the most linear is this one right here, which is the random forest model that was fully optimized. Here's a bar graph of all of the R-squared values of all of our models. And the best performing model was the random forest regression model after it was fully optimized. Now let's try out our product. So these are the input variables, thermal conductivity. We have weighted thermal conductivity, atomic mass, valence, entropy thermal conductivity, electron affinity, mean density, valence, and standard density, and weighted range. And now once I hit predict, it'll give a critical temperature that it thinks that these values will be cooled down to, and it'll also give some estimated material compositions. Yeah. So it predicts that based on all these values, the critical temperature will be 3 degrees Fahrenheit. And here's some predictions for the material composition. And that's it. Are there any questions?